CWIprep course, Ultrasonic Testing, Module 10, Part 14. Learning objectives. For this module, we're going to touch base on ultrasonic weld inspection, immersion testing, contact testing, general technique considerations, standard test blocks, reference blocks, phased array ultrasonic weld inspection, ultrasonic testing, record of inspection, and ultrasonic testing advantages and disadvantages.
Sound produced by vibrating body, a transducer, and then travels in the form of a wave. Similar to light waves, they can be reflected, refracted, and focused. Ultrasonic reflections from the presence of discontinuities or geometric features enables the detection and location of defects or discontinuities, depending on what you have. Here's another slide that gives you a general idea. The technique for inspecting butt welds with shear waves. You're just sending a sound wave in there, and if there's no defect, the sound wave just continues on. But if there is a defect, it's going to kick it back, and it's going to show up on your ultrasonic test device on your screen as a flaw or a indication. Immersion testing. In immersion testing, a waterproof transducer is used at some distance from the test specimens, and the ultrasonic beam is transmitted into the material through a water path or column. The water distance appears on the display as a fairly wide space between the initial pulse and the front surface reflection because of the reduced velocity of ultrasound in water. Because of this distance between the transducer and the specimen, near field and dead zone type effects are usually minimal for immersion type testing. Also, with the transducer separated from the specimen and the coupling being automatic, the transducer is reasonably free to move, and therefore most automatic scanning methods are associated with the immersion testing method. In contact testing, the transducer is placed in direct contact with the test specimen with a thin liquid film used as a couplant. On some contact units, plastic wedges, wear plates, or flexible membranes are mounted over the face of the crystal. Transducer units are considered as being in contact whenever the beam is transmitted through a couplant other than water. The display from a contact unit usually shows the initial pulse and the front surface reflection as superimposed or very close together. Both near field and dead zone effects are present in contact type tests. Contact testing is divided into 3 techniques, which are determined by the ultrasonic wave mode desired. The straight beam technique for transmitting longitudinal waves in the test specimen, the angle beam technique for generating shear waves, and the surface wave technique for producing Rayleigh or Lamb waves. The angle beam technique is used to transmit sound waves into the test material at predetermined angle to the test surface. According to the angle selected, the wave modes produced in the test material may be mixed longitudinal and shear wave only, or surface modes. Usually the shear waves are used in angle beam testing, as shown in figure 6.4.5. This shows an angle beam unit scanning plate and pipe material. To reduce confusion from dead zone and near zone effects encountered with straight beam transducers, parts with a thickness less than 5/8 of an inch are tested with angle beam units. In this technique, the beam enters the test material at an angle and proceeds by successive zigzagging deflections from the specimen boundaries until it is interrupted by a discontinuity or a boundary where the beam reverses direction and is reflected back to the transducer. Allowances are made when placing the angle beam unit to account for the lessened effective length of the penetration because of the zigzag path taken by the beam. Angle beam techniques are used for testing welds, pipe or tubing, sheet and plate material, and for specimens of irregular shape where straight beam units are unable to contact all of the surface. Angle beam transducers are identified by case markings that show the beam direction by an arrow, and that indicate the angle of reflection in steel for shear waves. General technique considerations. Ultrasonic test preparations begin with an examination of the test specimen to determine the appropriate technique. Then components are selected from available equipment to perform the test. Many variables affect the choice of technique. For example, the test specimen may be too large to fit in the immersion tank. In the case of large fixed structures, the testing unit is moved to the test site. This may require portable testing equipment. Other factors are the number of parts to be treated, the nature of the test material, test surface roughness, methods of joint, welded, bonded, riveted, etc., and the shape of the specimen. If the testing program covers a large number of identical parts and a permanent test record is desirable, an immersion technique with an automatic scanning and recording may be suitable. One-of-a-kind or odd jobs may be tested with portable contact testing units. Each case will require some study as to the most practical, efficient technique. Ultrasonic equipment ranges from small portable units to large permanent facilities. Some are manually operated, some have been automated in several features to include automatic scanning of specimen and recording of the information. Basic A-scan, B-scan, or C-scan type of recording methods can be used. Special types of ultrasonic equipment can be obtained to measure thicknesses, speed of ultrasonic waves, or change in impedance. The degree of automation and the means of data analysis and types of data displays are constantly improving, and largely this is due to advances in computers and software. Along with the basic equipment, there are transducers, automatic scanning and manipulator systems, tanks, couplet materials, calibrations, and standard blocks that are necessary to support ultrasonic testing. In ultrasonic testing, discontinuity indications are normally compared to indication received from testing a reference standard. The reference standard may be any one of many reference blocks specified for a given test, or it may be an actual part to be tested containing a known or emulated flaw. So your ultrasonic test technician is going to take his machine and he's going to test it against a known quantity, a certain size flaw in a certain type of material. So if he's doing an ultrasonic test on a certain type of carbon steel, then he's going to go get a standard test block for that particular type of material, and then he's going to calibrate his machine to make sure he can find a flaw of a certain size and depth at a certain distance, and then he's going to know his machine's calibrated. He's good to go. But if he changes from carbon steel to aluminum or another material, then he's got to use a different test block with another flaw or hole or defect, manufactured defect or notch, whatever he's trying to find. He's got to switch over to that on that material. So once you get a machine calibrated for a certain type of carbon steel, you can't use it on stainless steel or a nickel alloy or aluminum or titanium. It's got to be specific. So you have to have specific standards and test blocks for whatever material you're testing. Ultrasonic standard reference blocks, often called test blocks, are used in ultrasonic testing to standardize the ultrasonic equipment and to evaluate the discontinuity indication received from the test part. Standardizing does two things. It verifies that the instrument/transducer combination is performing as required. It establishes a sensitivity or gain setting at which all discontinuities of the size specified or larger will be detected. Evaluation of discontinuities within the test specimen is accomplished by comparing their indications with the indication received from the artificial discontinuity of known size, and at the same depth in a standard reference block of the same material. Here's a reference block for UT, a drawing that I borrowed from Uncle Sam, vintage 1970s. But you can see that you've got variable sizes that you can make these. So you can make a flat bottom hole, and then there's different sizes where you'd make them of different sizes, and then you'd use the ultrasound to go down, bounce sound waves down there, and look for that hole of that size, and then it would tell you if your machine was calibrated to find a hole of that size at that depth. So you just set it off of this table. So if you want a 1/4 inch at at a certain depth, you make a block like that, or you buy them. Here's another reference block for UT. It's got all kinds of notches and grooves built into it, so you can find, a 2-inch diameter hole or a 6/100 inch hole. There's various sizes, and it tells you angles and whatnot, but there's a lot of these different blocks, and this is a reference block that you can use to calibrate UT. And I'm not an expert on this, so I can't give you a lot of information in regards to what exactly they do with these, but it is a reference block, and there are a lot of different sizes and uses depending on which code you're using and what you're looking for. Angle beam testing and scanning a weld. We're going to look at a couple of diagrams and slides here, kind of give you a general idea of what goes on when they're searching for flaws in a weld using the ultrasonic method. This is an angle beam method as shown in 1112. As you can see in figure 1112, the sound beam passes through the wedge and enters the part to be tested at an angle. The sound beam will continue to bounce at this angle until it is completely scattered or absorbed by the material. Weld inspections are performed when the sound has made only 1 or 2 bounces. If a flaw is present in the weld, as indicated in figure 1112, some of the sound beam will reflect back and show up as an indication on the CRT screen. The best scanning method is to move the search unit forward and backward, alternatively approaching and move away from the weld at a distance sufficient to permit the sound to pass through the full thickness of the plate and the weld in an upward and downward path. The search unit is also moved parallel with the weld itself as shown in 11-13. In this manner, you will scan the complete volume of the weld following the same pattern along the weld as shown by the dotted line in figure 11-13. So what's that telling us? It's telling us that you're going to do a zigzag pattern back and forth, and if there's a flaw in there, some of the sound energy that you're kicking into that, sending into the plate, is going to get sent back to you. If there's no flaws in the weld, you're not going to see anything. But this is why you need a really skilled operator. This is, the number of hours required to become a good ultrasound technician is a lot larger than to become a visual weld inspector or use mag particle or dye penetrant. And it's because of this, because there's a lot of interpretation involved in, did I just see a back reflection or did I really see a flaw? But this is the general idea behind weld inspection with ultrasonic. You've got the transducer, you're sending sound into the weld or into the plate in the weld, and then here's a porosity and slag indication in a weld seam. You can see it's showing up on the CRT, vintage 1985, but gives you an idea of how ultrasonic testing works and how defects are found. Here's one where you can use a transducer on a weld where the weld has been ground flush. You can see that in the left-hand side. And then you've got the same thing that we were talking about in the other previous 3 slides on the right-hand side, where you've got the transducer and you're scanning the weld, and it's giving you a pattern. You know, there's different patterns. Depends on what you've got going on as far as the ultrasonic test procedure. So it gives you, this should give you a pretty good idea of what's going on. You're not going to be an ultrasonic test inspector, but this gives you an idea of what's going on and how the process works and what the general idea behind it is. All right, we're going to touch base on phased array ultrasonic weld inspection just for a minute. I'm going to hit it out of the Wikipedia page. The principle of operation for phased array. The phased array probe consists of many small ultrasonic transducers, each of which can be pulsed independently. By varying the timing, for instance by pulsing the elements one by one in a sequence along a row, a pattern of constructive interface is set up that results in a beam at a set angle. In other words, the beam can be steered electronically. The beam is swept like a searchlight through the tissue or the material being examined, and the data from multiple beams are put together to make a visual image showing a slice through the object. Phased array used in the industry. Phased array is widely used in several industrial sectors, such as construction or power generation. This method is an advanced NDT method that is used to detect component failures, i.e. cracks or flaws, and thereby determine component quality. Due to the possibility to control parameters such as beam angle and focal distance, this method is very efficient regarding the defect detection and speed of testing. Apart from detecting flaws in components, phased array can also be used for wall thickness measurements in conjunction with corrosion testing. Phased array can be used for the following industrial purposes: inspection of welds, thickness measurements, corrosion inspection, and flaw detection. So phased array is basically the old school ultrasonic testing, but they've hopped it up by using a bunch of small transducers, which each shoots out a sound wave independently. Then that information is taken back to the computer, and it gives you an image. Similar to medical testing. That's phased array, I'm pretty sure. Where if you and the wife or girlfriend or significant other are going to have a child, and you go in and they do the ultrasound on her, same thing, except with a weld. It's just, instead of giving you just a spike on an indication on a CRT, here they're giving you an image, and it'll give you an image of what's in that weld. A lot of this is due to the ability of computers to process massive amounts of information. All right, we're going to touch base on phased array ultrasonic weld inspection just for a minute. I'm going to hit it out of the Wikipedia page. The principle of operation for phased array. The phased array probe consists of many small ultrasonic transducers, each of which can be pulsed independently. By varying the timing, for instance by pulsing the elements one by one in a sequence along a row, a pattern of constructive interface is set up that results in a beam at a set angle. In other words, the beam can be steered electronically. The beam is swept like a searchlight through the tissue or the material being examined, and the data from multiple beams are put together to make a visual image showing a slice through the object. Phased array used in the industry. Phased array is widely used in several industrial sectors, such as construction or power generation. This method is an advanced NDT method that is used to detect component failures, i.e. cracks or flaws, and thereby determine component quality. Due to the possibility to control parameters such as beam angle and focal distance, this method is very efficient regarding the defect detection and speed of testing. Apart from detecting flaws in components, phased array can also be used for wall thickness measurements in conjunction with corrosion testing. Phased array can be used for the following industrial purposes: inspection of welds, thickness measurements, corrosion inspection, and flaw detection. So phased array is basically the old school ultrasonic testing, but they've hopped it up by using a bunch of small transducers, which each shoots out a sound wave independently. Then that information is taken back to the computer, and it gives you an image. Similar to medical testing. That's phased array, I'm pretty sure. Where if you and the wife or girlfriend or significant other are going to have a child, and you go in and they do the ultrasound on her, same thing, except with a weld. It's just, instead of giving you just a spike on an indication on a CRT, here they're giving you an image, and it'll give you an image of what's in that weld. A lot of this is due to the ability of computers to process massive amounts of information. Record of inspection for UT. Anytime UT is done, anytime any non-destructive testing is done, there should be a record of inspection. Good, clean paper trail. You'd need the operator's identity, the date, instrument identity, transducer type, sizes, frequency, and angle, identification of the test object, location of the weld, type of the material, thickness of base plate, type of joint and configuration, condition of the weld bead when you did the inspection, couplant, flaw data, inspection coverage, including reference points. All of these are pretty self-explanatory, but you just want to give somebody a trail of breadcrumbs so they can understand what you did, how you did it, why you did it, and if they need to redo it, they can do it the same way and understand how you did it. So this is just a little caveat in there on, record of inspection, one of the all-encompassing items that needs to be included. This is a record of inspection for any inspection that's done, visual, mag particle, radiography, whatever. There needs to be a clean paper trail. Ultrasonic testing advantages, disadvantages. We're going to talk about advantages. Internal inspection method, it's the deepest penetrating method. Can be adapted for thick or thin panels. Extremely sensitive to many specimen variables. Porosity, delaminations, micro cracks, geometry, density changes, grain or fiber size, and orientation. Many test control variables. You can have transducer frequency, transducer size, transducer types, transducer focal lengths, and type of test, immersed, contact, or jet. Ultrasonic testing, UT, advantages and disadvantages. Disadvantages, nonlinear responses, variable relationship between flaw size and indication size. Sometimes too sensitive, impossible to separate out the desired parameter. Often limited by geometry and surface roughness. Often must have special standards, especially when details are as small or smaller than the width of the inspection beam.
Summary. In this module, we covered ultrasonic weld inspection, immersion testing, contact testing, shear waves, general technique considerations, standard test blocks, reference blocks, phased array ultrasonic weld inspection, ultrasonic testing, records of inspection, and ultrasonic testing UT advantages and disadvantages.